Getting back to audio synth experiments, I'm going to try building the sub-octave generator that I simulated in LT-Spice recently. That's based on a 555 oscillator and then some flip-flops to divide the frequency by 2 each time it goes to another flip-flop in the chain. And every time the frequency is divided by 2, the tone produced is 1 octave down from the previous tone. It doesn't really matter exactly what part values I use for this. I'm going to use a potentiometer to do the 555 frequency. So if I'm going to make the 555 frequency variable anyway, I can use whatever capacitors and resistors I have on hand. These are parts I've had for a very long time. All these capacitors, some were bought new, some might have been pulled out of old equipment. There's all kinds, but I chose a bunch of 0.1, 0.01, and 0.001 micro, and I'm going to try using a single supply instead of a split supply for the op-amp. So from a single 9-volt battery, I will connect plus and minus across the op-amp power, but then I need to use 2 resistors of the same value to shift the non-inverting terminal up halfway, 4.5 volts, so that the input signal can swing around that. And then I don't need a dual supply plus and minus 9. Another thing I want to try using, this LM386 audio amplifier I've had for a long time and haven't used yet. So it's got an LM386 surface mount version, and of course output screw terminals for the speaker and a potentiometer for volume, I assume. And we have ground and VDD in and ground and audio in. So nice DuPont cables will help me out with this, and hopefully that will make it nice to hook everything up to a speaker and drive it properly instead of having to drive it from the output of an op-amp that may not be able to handle the load. This is where I left off with the LT-Spice simulation of the 555 tone generator oscillator, where I can generate a clock out, or a tone if it's within hearing range, send it in to the clock of a flip-flop hooked up this way so that the Q output, we're going to call Q0, is going to be half of the clock frequency, and then you take that flip-flop's output, clock the next one, so its Q1 output is going to be half of Q0, and so on. So each time you go along adding another flip-flop stage, you divide the frequency by 2 again. And this is a ripple counter, where the clock of each successive stage is clocked from the output of the previous flip-flop. Instead of all being run synchronously from the same clock, they are asynchronous. One's clocking the next, and it gets slower and slower. So these values here that I chose for the timing on the 555 were arbitrary for the purpose of demonstrating a signal and showing it gets half the frequency at the Q0 output. And when I experiment around generating tones on the workbench, I'm just going to do whatever based on parts I have laying around, and I will eventually come and fix this diagram up to match what I've come up with. Over here for the op-amp, I'm going to be changing this from a dual plus and minus 9-volt split supply into a single 9-volt. So I'll put a voltage divider on this non-inverting input, and all these 10K resistors are probably going to get changed based on what I have available and what I need to do to the signals to get them to work out in my setup. One thing I want to do is have a lot more than just 3 flip-flop stages for the Q outputs of the ripple counter, but I don't want to just have a whole pile of chips stringing together flip-flops. Instead, I'm going to use a 4040 chip. There's a series, 4020, 4024, and 4040. These are all CMOS ripple carry binary counters / dividers. So the 4020 is a 14-stage, 4024 is a 7-stage, and the 4040 is a 12-stage. So just looking at the 4020 with 14 stages versus the 4040 that I'm using with 12 stages, this is a 16-pin package, and so is the other one with 2 extra stages. What they do is they don't give you all the stages. They let you have Q1, they don't give you Q2 or 3, but then they give you 4, 5, and so on, up to 14. So you're missing a couple of those stages. I guess if the intent of a circuit is to have a big divider where you need a couple of more stages of flip-flops, you would use this. But I want to be able to get in all of these intervals. So if I have just Q1 and then I go to Q4, musically I'm missing 2 octave notes. So I'm going to use the 4040. So I got everything for 12 stages, Q1 through Q12 with nothing missing. So I take my 555 output, and pin 10 is the input pulses, and then all of these outputs correspond to all of these outputs here, except it's all in one chip package. So if I can find a SPICE model for a 4040, maybe I can replace this and show more accurately what I'm going to be doing now. And I also need to update everything else to show what I end up with today. The op amp I want to try first is an LF351 because I had it on hand. So I'm going to use all these little breadboards. I can't find any individual 555 chips, so I'm going to use a 556. I've had this chip a very long time, probably since the 80s. Now this is the major change I'm going to try for this experiment compared to the LT SPICE simulation. I happen to have a 4040 chip. This is like having 12 stages of flip-flops chained up in a row. So all I got to do is send the 555 clock in, and then I just have 12 individual outputs that each are going to be half of the previous flip-flop's frequency. So I'm going to go and try to build some of this and see if I can get it working. So this is how the circuit ended up after several hours of messing around. I'm using a 9-volt battery, and the 556 chip actually turned out to be weird. It wasn't really working, so I actually found a 555 after all and put it on here on the white breadboard. So it's your standard circuit with the resistor, a potentiometer, and a capacitor. The potentiometer is mounted on the little breadboard, so the 9 volts comes into this board. I want it to use the power strips, and then I just pass it on. So this is the output of the 555. I bring it over to the edge of the board and then jumper it on to the next board. So the power comes in, and I have a decoupling capacitor here. It was needed. The thing was squealing without it, even though it's still long wires to get across VCC and ground pins. It made all the difference in the world. So the main clock from the 555 comes to the clock input of the 4040, and then I tapped into the first 5 or so Q outputs, and I brought those over to this little breadboard so I could easily tap into them. So starting up here on the right would be the main 555 clock, and then each one going left is Q0, Q1, Q2, etc., dividing down the main clock by half each time. So musically, each time an output is taken one step away from its neighbor, it changes by 1 octave. And then if you change the main frequency of the 555, everything changes by relative pitch. So it stays locked and still sounds musically intact. So these are basically the outputs of the 4040 are basically tone generators. So I have a couple of stray wires. I made 3 for now, so I could just move them between the outputs as I want. And those go to this other small breadboard, and that is the op-amp mixer. I ended up using 22K resistors on the input of each channel on the mixer, and a 2.2K resistor on the feedback of the op-amp. Then I put a 0.1 micro DC block series capacitor at the output of the op-amp, and it goes over to the input of this 386 power audio amp and to the speaker ultimately. So let's see how it sounds. So here I set the 555 to something about 5 kilohertz arbitrarily, and starting up here on the red wire and going downward, I've got the main 555 clock, and then the outputs of the 4040 ripple counter. So starting at 5 kilohertz, every time we go down through the ripple counter, we should be reducing the frequency in half, and that would correspond to an octave drop in the tone if we listened to it. So the main 555, it's about 5 kilohertz. So if I go down to the first Q0 output, I should see about 2.5 kilohertz, and there it is. If I go down to Q1, it should be around 1.25 kilohertz, and there it is. If I go down again, it'll be half of that. Notice I chose not to do math. So it's showing 630 to 640 hertz. It's gonna flip around a bit. We go down half of that, it should be 3 something, and we got 320-ish. And then we go down one more time, and we got 160. Here's my 3 channels of the mixer. It doesn't matter which is which, they're all just waiting for an input. So the highest pitch we're going to get is going to be the main 555 clock signal. And I just arbitrarily chose values I had around, so it doesn't go as low as I would like normally for an oscillator, but we're dividing it down anyway, so it's going to just go down to clicks eventually anyway. So here's how the main clock sounds. So, you know, a standard boring single tone, right? So the next, if we go along, we should be hearing the frequency divided by 2 each time, and it should be an octave or so difference. There might be a little bit of detuning, especially when we start adding more sound channels, because the frequency, I believe, is going to be voltage dependent on the main power supply to some degree, and as we cause more loading, the battery is going to be draining a bit. But generally speaking, we should be hearing an octave difference as we go along. So it gets down to a click, and then there wasn't much point in having any more channels. So if we try and put 2 on at the same time, see what happens. Before I mix channels together, let me just pick one of these lower ones and see what kind of adjustments I can get on the tone, because on the highest one I couldn't go down very low. So I'm just going to pick the highest frequency from the 555 itself and just take another wire and mix in something else. So you can kind of hear there's 2 tones there. And that's where you could hear when I took out the main 555, the pitch changed a bit because I think it's just the loading on the battery. So when I put the main 555 higher pitch and then I add another octave down, you can kind of hear how they mix. And when you adjust the frequency up and down overall, it sounds a little more interesting than the single note. So if I want to add a third one, starts to sound more Atari-like. So I'll just randomly pick some, see what happens. That's all fine, but ultimately I want to turn this into a sound effect generator as well, and I guess one step in that, a light-dependent resistor hanging out on a Lego-style mini breadboard. Let me plug that in parallel with this pot, see how that goes. Turn off the light. So let's add some more channels. So basically, I don't even think we need the potentiometer if this is in parallel. I think this is a 100K pot, right? And this is maybe, I don't know, 30-something K average. In parallel with 100K makes it negligible. So it's just this doing the work. So already I can see the potential for making weird sound effects and having things interact a certain way, more than just a boring keyboard that happens to track itself with octaves. Lots more experiments to come. Like, I gotta still add a filter to this and see how that sounds if I can change the contour on top of all the complex tones that are being generated. And I will see what I can end up coming up with. I've got some other ideas about how I can maybe take some other signals here and use them as feedback in the system and help kind of make a weird noise or effect based on what's going on in the circuit. I might redo some of this more permanent now that I've tried it all out and I see what blocks I might want to keep and just get them all on one breadboard consolidated, because it is all kind of hard to organize here, especially if I want to move this away temporarily and then bring it back to work on it. So using all these separate tiny breadboards for things like keeping individual circuit blocks separate and interconnecting them as needed, bringing things in and out of circuit if I want, and also using them as access terminals like this one. It's a good idea in the beginning, and then when I figure out what I'm doing, you know, maybe I can move this 4040 circuit over here now because it's pretty much just power and a clock input. I don't need that on its own breadboard. It can go right here and it'll never really change as a circuit block. It's going well so far. I don't really have a goal in mind. I'm just experimenting with all of this and see what comes of it.